Okay, let's look at the keywords. Use a highlighter here. A beam has mass 12 kilograms, length 5 given in the question, equilibrium, got 2 vertical ropes, so we're going to get a tension. We can see it's attached to A and C, BC equals 1 meter, and it's an uniform rod. That's the main thing. Light strings means no weight on the strings. So let's label what we can. So it's uniform, so the centre mass is in the middle. It's 12G. And let's be clear, let's make that 2.5. That's 2.5. Wonderful. The tension, that's C. So I'm just going to call that TC, TA. So holding equilibrium, we need to find this tension C here. So we want to take the moment about A, because that will cancel that out. So what have we got clockwise? Moments about A. We've got clockwise 2.5 times 5. Not 5, 12G. Now it's in equilibrium, so that's got to equal the anti-clockwise movement or moment. So that's going to equal, well, the whole thing's 5 and that's 1, so it's going to equal 4 times TC. So I'm just going to call that 4TC. So that's 30G equals 4TC. So that's going to equal 7.5G equals TC. And that equals 73.5 newtons. That's that done. Very easy. The tension in rope at A. Now, remember in the past, we said let's resolve vertically, because then we know we have TA plus TC equals 12G. The downwards. 12G is the downwards, right? Now, because we've got TC already, we can do this. So we've got 73.5 plus TA equals 12G, and you can just solve it. So TA equals 12G minus 73.5. What does that equal? 44.1. And that one is newtons. That's quite easily done. That should be a full 5 out of 5 marks. Now let's have a look. I've underlined the keywords. Well, hopefully you can get these 3 marks. Let's just start. We've got a mass of 16 kilograms and it's attached to a beam at a point which is Y meters from A. So that's A. I'm going to call that Y, and that's 16G. So we still need to take moments, and we want the new tension at C, so it would make sense to take the moment around A, because that cancels out the TA. So let's look at the clockwise, and then also it's a moment about A. So we have Y times 16G plus the 2.5 here times 12G, and let's just gonna, you don't need brackets, but let's just keep that together, and that's got to equal the anti-clockwise from the tension here, and that's 4. Remember, from here to is 4, so that's I'm just going to call it 4TC. So what do we get? We get 16GY plus 12 plus 30G, and we know that from before. We've got the 4TC here, so it does link. The skills are the same. That's going to get you some effort marks. Now it says in terms of Y, well, you just divide everything by 4. So TC equals at 7.5G add 4GY, and then you could just say, put that in newtons, so that's 39.2Y plus 73.5 newtons, and that's just multiplying a G equals 9.8. There. That's part B done. Let's look at C. The rope at C will break if the tension exceeds 98. The rope at A cannot break. Find the range of possible positions on the beam where the load can be attached without the rope at C breaking. So TC, that's part C. Let's remember that was part B and that was part A. TC has to be less than or equal to 98. So we can just use this. 39.2Y plus 73.5 has to be less than 98 equal to, and you just solve that, and we can all do that. So Y is less than or equal to 0.625, hence the load then 0.625 meters from A, and that's it. That's just your answer mark, and using your communication skills there. Okay, so let's see. We have a mass of 8 kilograms and a mass M. It's uniform and it's in equilibrium, and they've given us all the details here. So M is attached to the rod at B, so remember the mass, so it's mg. That's going to be 0.75, and then we're going to get 8g. Show that m equals 2. Well, it's in equilibrium, so clockwise is going to equal the anti-clockwise moment. So we're going to take moments about C. So that's 1.5 and that's 0.9. That's 0.6. Let's do the clockwise. So we're going to get 0.6 mg equals, what's this bit here? That's going to be 0.9 minus 0.75. So that's 0.15. So we're going to get 0.15 times 8g and 0.6 mg, and divide out by 0.6 g, and that's going to give equal 2 meters. M equals 2 meters. That was a very nice question. So let's look at part B now. We need the distance AD. So you've got a particle of mass of 5 kilograms. It's now attached to the rod at A. So let's write 5G here. And the support is moved from C to point D of the rod. The system, including both particles, is again in equilibrium with AB horizontal. Find a distance AD. So we can call this X or leave it as AD, whatever you prefer. But I could just leave it as probably X. Now think about it. If you're adding a weight here, and that's important, for this to stay balanced, this C here will have to shift this way, so that the new moment at D, because if it shifts further this way, the clockwise moment at the pivot will be smaller due to the distance times the force. So for it to be balanced, it should make sense that D will move this way, and that's quite important for your calculations. So that's D there. I want to write moments around D. Now let's think that anti-clockwise is going to equal the clockwise. So you need to get good at this. So this is the anti-clockwise this way. So we've got 5gx is going to equal, what have we got clockwise? D has moved and we've still got the centre of mass. So we've got 8g times something. Now remember, this bit is 0.75. So here to here must be 0.75 minus x plus, so what's this length? 2g times 1.5 minus this x, right? Minus the x. Now expand and solve. So we're going to get 6g minus 8gx plus 3g minus 2gx equals 5gx. That's minus 10. So when we resolve that, we're going to get 15gx equals 9g. By simplifying that, so let's divide out by 15g now. Divide by 15g. So x equals 0.6. So AD equals 0.6 meters. That should make sense to you, and hopefully you're getting really good at these skills now. Okay, give yourself some time to read this question. A lever consists of a uniform. What do we know there? Well, the centre of mass is going to be in the middle. It has weight 100 newtons. So weight, remember, when they give you a mass, you have to use G, because gravity is applied. But that's just 100 newtons, so you don't need to put a G there. And that's going to be 1 metre in. That's a good start. It rests on a smooth pivot at a point C. That's here. Lovely. A load, so that must be 2,200. The lever is in equilibrium, but there's a vertical force applied at A. The rope is modelled as a light string, so just consider that going like that, and we don't know what that is. Given that BC equals 0.2, right, that's valid information. 0.2. Find the magnitude of the force at A, because the force at A is keeping it in equilibrium. So we want to take moments about C. So MC. So let's do the clockwise first. So that's 0.2 times 2,200. You can see that's clockwise, making a clock spin around. So 0.2 times 2,200. Step 1. that's going to equal everything this way, so we've got this. So that must be 0.8. So equal 0.8 times 100. Add 0.8 is 1.8 times, I'm going to call that A. So what do we get? We get 440 equals 80 plus 1.8A. Now let's solve that. So we're going to get 360 equals 1.8A. Divide out by 1.8, so A equals 200. Not bad at all. And just remember that is going to be 200 newtons because that is a force. Now that should be an achievable 4 out of 4 marks for you. Right, so let's look at part B. The position of the pivot is changed, so the rod still remains in equilibrium, but the force at A changes to 120. So I'm going to use the same diagram, 120. Now if this number is less from 200, then to make this moment, which is anti-clockwise, we have to think which way is this pivot going to move. Now it should make sense. If this is less, then the pivot has to move here because you're going to need a greater force times distance here. So the distance has to increase. So let's begin. Let's take moments about the new point C. This is the new C. So what we're going to have, the 120, so that's the new C. Now that's going to be times 2 meters, because you know the whole thing is 2 meters, and then we've got a new distance here, x, so that's minus x, plus this one, which is going to be 100 times 1 meter minus x equals, we've got the x here, so it's 2,200 times x. Let's expand that out. 240 minus 120x plus 100 minus 100x is going to equal 2,200x. So we're going to get 340 minus 220x equals 2,200x. So 340 equals 2,420x. So x is going to equal 0.14. Now the distance is in meters, so that is 14 centimeters. And that is easily doable for you. So well done, that should be 5 out of 5. Good work. And you need all this writing to get your full method and answer. So let's see. There's a beam and it's supported by a smooth pivot. So there's no friction on the pivot. The jaw is mass 25. So let's write 25g because it's mass and not weight, and David is 40. And he sits at a distance x from C. The beam is initially modelled as a uniform rod. using this model. They haven't given you a mass of the rod, but anyway, let's just do this. Find the value of x, but because C is in the middle, I guess we don't need to use it because we're going to take moments about C, I imagine. Find a value for x which the seesaw can rest. So that means where can David stand away from C so that it is in equilibrium. So we take moments about C. So we're going to get this way, that's anti-clockwise. You can get 25g times 2, because we know that's at the centre, so that must be 2. And that's going to equal 40g times x. So you're going to get 50g equals 40g times x. Divide out by 40g, which is going to give you 1.25, because you are going to get 5 over 4, equals x equals 1.25 meters. That's an easy 3 marks. State what is implied by the modelling assumption that the beam is uniform. So what does that mean? Well, we know that, so the weight acts at the centre of beam, right? And beam, well, you can get more technical and say, well, the weight is evenly distributed across the beam, so the weight or slash mass acts at midpoint. Right, C. Well, David realises the beam is not uniform and he must sit a distance at 1.4 meters from C. So let's change this and write 1.4. And it's now modelled as a non-uniform rod of mass 15 kg. Using this model, find a distance of the centre of mass of the beam from C. So have a think about what moments you need to do or take. Where can I write C? I'm going to write C here. So if that's 1.4 meters, there's going to be 15g somewhere around here. Now how can I explain that? Right. So let's think about it. It's got to be around here, because if David is actually still 40g, what's 1.4 times 40g? That's 60 G. $56G. So 56G, can you see, is greater than 50G if you're not sure. So this will pull this seesaw down, but it's still in equilibrium, so the seesaw is still in the middle, the pivot is still in the middle, so this weight must be here to get the extra 6G. So we take moments about C again, MC. So we've got David, which is 40g times 1.4. Now that's going to equal, so that's the clockwise here. Now C is still in the centre, so we've got 15 times YG here, or 15GY, plus Jill 2 times 25g. So we get 15gy plus 50g equals 56g. So 6g equals 15gy because we're minus 50g on both sides. And divide out by 15g and you'll get 0.4 equals y. So the distance from C is 0.4 meters. And that is done. So let's look at this question. Pause the video and have a read if you want, but I can see the length is 4 meters. This diagram is not labelled. Jack and Jill are playing with the plank, and Jack has mass 40, Jill has mass 25. Do make sure you label the numbers correctly, because I have made mistakes in the past where I just put the wrong number down for some reason. BC equals 1.6 meters, plank is in equilibrium, Jack and Jill are particles, and the plank is uniform. On the point of tilting means the moment clockwise and anti-clockwise are going to equal. So let's now fill in those details. So Jill is here and she weighs 25g, her mass to be correct, her weight will be 25g newtons. And Jack is 40g, and there's Jack. Okay. Uniform rod, B to C is 1.4. No, 1.6, see that, be careful. The whole rod is 4 meters. And the centre is here, and it's got a mass of mg. That's at 2 meters. And remember, C is this pivot here. So we're taking moments about C. Let's go clockwise. So what are we going to get? We're going to get 1.6 times 40g. And that's going to equal the anti-clockwise. If this is 1.6, the middle is at 2 meters. From here to here is 0.4. So we're going to get 0.4 times mg plus 2.4, because that's 2, add 0.4, so plus 2.4 times Jill's mass, which is 25g. Now I think that is 64g equals 2.4 times 25 equals 0.4 mg, add 60g, so we're going to get 4g equals 0.4 mg by subtracting 60g on both sides. So we just divide out by 0.4g on both sides to get the mass, and the mass will equal 10 kilos. Wonderful. Now for part B, it says they alter the position of the plank in relation to the platform, so that when Jill stands at B, Jack stands at A. So you can see here in my diagram how Jill's and Jack's positions are reversed. That's A and that's B. The plank again is in equilibrium and the point of tilting about C, so the clockwise is still going to equal the anti-clockwise moment. Find the distance BC in this position. And that's in relation to where Jill stands at B. So this mystery distance x it's going to be that distance B to C now. Now to get this right, you have to think, well, where is this going to move? On the edge of the cliff. But you can just model this as the pivot. Now if it's lighter on this side now, to make the moment the same, this C from here has to shift this way because the weights are swapped. That should make sense to keep it in equilibrium and to stop it from tilting. So we're going to make this assumption that C is beyond the midpoint 10G of the uniform rod, which is 2, 2. So let's take moments around the new C. So let's do this first. We have X times 25G. You could use a Y so you don't get the X's confused. Plus 10G, the weight of the rod. And can you see this whole length is X and that bit is 2 here? You're going to get 10G times X minus 2. Now that's going to equal 40. Now you have to get this bit right. What's the whole length of this whole thing? Remember, it is 4. So that distance has to be 4 minus X. So we get 25GX plus 10GX minus 20G equals 160G minus 40GX. Let's combine the GX's, so we get 35GX here minus 20G equals 160G minus 40GX. Let's get the GX's together, so you can see we get 75GX equals 180G. Now the G's cancel obviously, so X equals 180 over 75. So X equals 2.4 meters, and we are done. State how you've used the modelling assumptions that the plank is uniform. Well, when it's uniform, the weight, or technically you can say mass, acts at centre or midpoint, centre of plank. Plank is a rod, so that just means the plank remains straight and doesn't bend. Jack and Jill are particles. Oh, the weights act at the end of the plank. Weights slash mass acts at the end of the plank, and hopefully that's going to help you guys out so much, and you're going to really improve your moment skill. And the skills are generally all the same in all the types of questions, and there's plenty there. Do practice these and get really good, because it's so easy to make a little calculation error, but do hit those method marks at least and perfect getting those answer marks. Well done.